We're going to start talking about, we now have the ability to think about electric and magnetic effects on a single moving charge, okay? And one particularly useful application we'll see is a situation where you have what's called crossed electric and magnetic fields. Where you have a situation that looks like this. You have a magnetic field pointing out, for example, and an electric field pointing down. So they're at 90-degree angle to each other, okay? And then we're going to send a charge, positive charge, moving through this region. We can say a uniform magnetic field pointing out, a uniform electric field pointing down. We send a charge through the region that through this region where the velocity is perpendicular to both of those fields. So E is at a 90-degree angle to B, and then V is at a 90-degree angle to both the magnetic and electric field. So here's a little table. Think about the direction of the electric force on this charge and the magnetic force on this charge. There are four choices, 1, 2, 3, 4. Which of those choices is the gives the correct direction for the electric and magnetic forces? So we got. Okay, most of us are saying that upon a positive charge, we have the electric force pointing down. Okay, that just comes from electric forces being equal to Q times E, right? If the electric field is pointing downward, when you have a charge in that electric field and the charge is positive, you multiply positive by the electric field, you get a vector that's in the same direction as the field, okay? So the electric force is pointing downward. Magnetic force turns out to be pointing upward, right? Because we have velocity pointing in that direction. Magnetic field is out. V cross B is up. Multiply by a positive charge, and the vector is still pointing up, okay? So we end up with this in this funny situation where with crossed E and B fields, we end up with the electric and magnetic forces pointing in opposite directions. Okay? Everybody okay? Questions? So let's change the sign. Same situation, only now it's a negative charge. What happens? Okay, so it's got to be the reverse, right? The electric force is now pointing up because if you multiply the field by a negative number, you get a force in the opposite direction. So we've just flipped the direction of both of them. Okay, magnetic force pointing downward. Q or V cross B is still up, but when I multiply by a negative charge, I flip the direction, get a magnetic force pointing downward. Okay. So this is kind of interesting. We have a situation where we can get, no matter what sign of charge we pick, we get a situation where we can have these two forces in opposite directions. If I could arrange things in such a way that the forces were equal to each other, what would be true? What would happen to the charge? It would just move in a straight line, right? The net force on it would be 0, okay? Newton's second law tells us if the net force is 0, the momentum of the charge, and therefore the velocity, isn't going to change, okay? No acceleration on it. We'll just travel at a constant velocity. So what's got to be true? Let's say we have a charge Q, traveling in a straight line at a constant speed. What's got to be true? Okay, most of us are saying, although there's some disagreement here, that QE is equal to QVB. So again, well, we kind of gave the answer away, but before we talked about it, but the idea is that the net force on the charge has to be 0, right? So let's just be really formal about this. If we have a rate of change of the momentum, or alternatively the mass times the acceleration, dv dt, is equal to the net force on the charge. We want the acceleration to be 0. That means the net force has got to be 0. And on this charge, there are two forces, an electric force and a magnetic force. Okay? So those two forces have got to be in opposite directions and equal in magnitude, right? So let me just look at the magnitudes. We already know they're in opposite directions. The magnitude of the electric force is the charge times the electric field, right? The magnitude of the magnetic force is the charge times its speed times the magnetic field times a sine of what angle? 90 degrees, so sine of 90 is 1, so it's just going to be Q times V times B. And so answer 1 is correct, but let's see. Okay, there weren't any other choices here. So 1 is correct. It's not going to be that the electric field is equal to the magnetic field. There's no relationship here that says that. Q times B is not the magnetic force, right? It's got to be Q times V times B. And what do you notice in this expression? What happens to the charge? It cancels out. It cancels out. The electric field is equal to V times B. So it turns out that the speed, if given a situation where the electric field and the magnetic field are perpendicular to each other, and you know the magnitude of the electric field and you know the magnitude of the magnetic field, any particles that travel through, or any charged particles that travel or enter this region with a speed of E over B, will go through at a constant speed, okay? We'll go through at a constant speed because that's sort of the magic speed you would need for the two forces to be equal in magnitude and opposite in direction, okay? Let's just try a calculation, for example. And notice that the charge divides out, so the sign's not even going to matter, right? So let's try this. Particle travels in a straight line at a constant speed. What's the speed of the particle? We know the electric field is 1,000 volts per meter. The magnetic field is half a Tesla, 0.5 Tesla. The charge is negative 3.2 times 10 to the minus 19. So it's like a doubly charged ion, for example. What would be the speed of the particle if it travels at a constant speed? All right, clearly 2,000 meters per second, right? We just worked this out. So let's think about what would happen if you had a particle. So here's the electric field, 1,000 volts per meter, magnetic field, half a Tesla, and a particle traveling through at 2,000 meters per second would go through at a constant speed, constant velocity, okay? What would happen if I had a charge moving at 1,000 meters per second? Would it travel through at a constant velocity? No. What would happen to it? It would drop. Why would it drop? Because the magnetic force and electric force would be different, and which would be bigger? The electric force, right? Because the magnetic force depends on the speed. It's Q times V times B, whereas the electric force is just Q times E. The electric force is going to be constant no matter what speed the particle is. So if the speed is too low, the magnetic force is going to be small, and the electric force would be larger. Well, in fact, for a negative charge, it would be the other way. It would actually rise because the electric force would be upward. So let's just look at a positive charge for simplicity. If it were a positive charge, the electric force would be bigger than the magnetic force, and this charge would be deflected, right? It would go downward. If you had a charge moving through with a speed of 3,000 meters per second, what would happen? It would go upward, right? Because now the magnetic force would be bigger than the electric force. So what we've just created is something called a velocity selector. Meaning you can select a charges of a particular velocity. Anything moving, in this particular case, anything moving faster than 2,000 meters per second would be deflected upward. Anything moving slower than 2,000 meters per second would be deflected downward. And so downstream, you'll only get out of this device particles moving with a precise value of 2,000 meters per second, or whatever E over B happens to be equal to. Okay? And this has technological applications. We talked last time about the mass spec, where you can relate the radius of curvature to the velocity. Well, if you only want certain velocities to go through, so you can easily measure the radius, you can add a velocity selector to your device to make sure only certain velocities get through. Okay? We will use this idea in a number of different applications when we get back from break.